so we move on to another identity that you've been working on based on the calculation of what is A cross B dot A cross B. If these things are operators, there's corrections to the classical formula for the answer of this, of what this product is supposed to be. Actually, the classical formula, so it's not equal to A squared B squared minus A dot B squared, but it's actually equal to this plus dot, 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 a few more things. Classically, it's just that. You put two epsilons, calculate the left-hand side, and it's just these two terms. Since there are more terms, let's look what they are for a particular case of interest. So our case of interest is L squared, which corresponds to R cross P times R cross P. And indeed, it's not just R squared P squared minus R dot P squared, but there's a little extra, and perhaps you have computed that little extra by now, is IH bar R dot P. So that's a pretty useful result. And from here, we typically look for what is P squared. Solve for P squared. So what we do is pass these other terms to the other side. And therefore, we have 1 over R squared, R dot P squared minus IH bar R dot P. Yes. Plus 1 over R squared L squared. And, you know, we've done this with some prudence. The R squared is here in front of the P squared. It may be fairly different from having it to the other side. Therefore, when I apply the inverse, 1 over R squared, I apply it from the left, so I write it like that. And that's very different from having the R squared on the other side. Could be completely different. Now, what is this? Well, there's this is a simple computation when you remember that P vector is H bar over I gradient. And R dot P, therefore, is H bar over I R ddr. Because R vector is R magnitude times the unit vector in the radial direction, and the radial direction of gradient is ddr. So this can be simplified. I will not do it because it's in the notes, and you get minus H squared 1 over R d second dr squared R. In a funny notation, the R is on the right, and the 1 over R is on the left. And you would say, this doesn't sound right. You have here all these derivatives, and what is an R doing to the right of the derivatives? I see no R. But this is a kind of a trick to rewrite everything in a short way. So if you want, think of this being acting on some function of R, and see what it is, and then you put a function of R here and calculate it, and you will see you get the same. So it's a good thing to try that. So P squared is given by this. There's another formula for P squared. P squared is, of course, the the Laplacian. So p squared is also equal to minus h squared times the Laplacian operator. And that's equal to minus h squared times, in fact, the Laplacian operator is 1 over r d second dr squared r plus 1 over r squared 1 over sine theta dd theta sine theta dd theta, it's a little bit messy, plus 1 over sine squared theta d second d phi squared times closing this. So a few things are there to learn. And the first thing is, if you compare these two expressions, you have a formula for L squared. You have L squared in 1 over r squared on the upper right. And here you have minus h squared times this thing. So L squared, that scalar operator, is minus h squared 1 over sine theta dd theta sine theta dd theta plus 1 over sine squared theta d second d phi squared. So in terms of functions of 3 variables, x, y, and z, L squared, which is a very complicated object, has become just a function of the angular variables. And that is a very important intuitive fact. L squared, L is operator that's rotation, so it shouldn't really affect the r, shouldn't change r, modify r in any way. So it's a nice thing to confirm here that this operator can be thought as an operator in the acting on the angular variables, or you could say on functions on the unit sphere, for example. It's a good thing. The other thing that you've learned here, so this is a very nice result. It's not all that easy to get by direct computation. If you had to do Lx squared plus Ly squared plus Lz squared, first, all these possible order, well, there's no ordering problems here, but you would have to write this in terms of x and py and pz and x, y, and z, then pass to angular variables, simplify all that. It's a very bad way to do it, and it's painful. So the fact that we got this like that is very nice. The other thing that we've got is some understanding of the Hamiltonian for a central potential, what we call a central potential problem. V of r. Now, I will write a V of r like this, but then we'll simplify it. In fact, let me just go to the central potential case, which means that the potential just depends on the magnitude of r. So r is the magnitude of the vector r. So at this moment, you have p squared over there. So this whole Hamiltonian is minus h squared over 2m 1 over r d second dr squared r plus p squared over 2m, so 1 over 2m r squared L squared plus V of r. So our Hamiltonian has also been simplified. So this will be the starting point for writing the Schrödinger equation for central potentials. And you have the operator L squared. And as far as we can, we'll try to avoid computations in theta and phi very explicitly. but try to do things algebraically.